They all exist in the same plane, rotating in the same direction. You see, it is absolutely magnificent. It's almost supernatural. Astronomers, when talking about the solar system, no matter how hard you try, you will never be able to comprehend how small and spatially insignificant a proton is. It is simply incredibly tiny. A proton is an immeasurably small part of an atom, which itself represents something of very insignificant size. Protons are so small that a tiny dot over the Latin letter I contains about 50 million billion of them, which is significantly more than the number of seconds in 500,000 years. So, a proton is exceptionally microscopic, to put it more strongly. Now imagine that you somehow managed, although of course you wouldn't, to compress one of the protons to 1/1000th of its usual size, so that a normal proton would appear gigantic next to it. Pack about a tablespoon of matter into that tiny space. Great. You are ready to initiate the universe. I assume you want to create an inflationary universe. If instead you prefer to create a more old-fashioned universe of the standard Big Bang, then you will need additional materials. You will have to gather everything in the world, every last speck and particle of matter, from here to the edge of the cosmos, and cram it all into an area so infinitely small that it actually has a size. This is called a singularity. In both cases, prepare for a truly Big Bang. You would obviously want to witness this spectacle from some safe place. Unfortunately, you cannot step away anywhere because there is no where beyond the singularity. Once it begins to expand, the universe will not fill the surrounding emptiness. The only space that exists is the one it creates as it expands. It is very natural, but incorrect, to envision a singularity as something like a pregnant point hanging in dark, boundless emptiness. But there is no emptiness, no darkness. The singularity has no around, no space to occupy, and no place where it exists. We cannot even ask how long it has been there, whether it just suddenly appeared, like a lucky thought, or whether it has been there forever, patiently waiting for the right moment. Time does not exist. It has no past from which to emerge. And so, from nothing, our universe begins with a blinding impulse in a triumphant moment, so swift that it cannot be expressed in words. The singularity expands and takes on cosmic proportions, occupying unimaginable space. 1 second of life, a second that many cosmologists dedicate their lives to studying increasingly shorter moments, producing gravity and other forces that govern physics. In less than a minute, the universe reaches a diameter of 1,000,000 billion kilometers and continues to grow rapidly. At this moment, it is very hot, 10 billion degrees. This is enough for nuclear reactions to occur, generating the lightest elements, primarily hydrogen and helium, with a tiny addition of lithium, about 1 atom for every 100 million. In 3 minutes, 98% of all the matter that exists now or will ever exist is formed. We have a universe, a place with astonishing and inspiring prospects, and it is also very beautiful. And all of this happened in the time it takes to make a sandwich. When this occurred is a debatable question. Cosmologists have long argued whether the creation of the universe happened 10 billion years ago, twice as long ago, and only somewhere between these moments does the general consensus seem to lean towards the figure of 13.7 billion years. But, as we see later, such things are frustratingly difficult to measure. Essentially, all we can say is that at some indefinite point in very distant past, for unknown reasons, there was a moment designated in science as T equals 0. That's where everything began. Of course, we still do not know a great deal, and often think we know. But in reality, we do not, or we have thought so for a long time. Even the very idea of the Big Bang emerged quite recently. It has been discussed in detail since the 1920s, when Belgian astronomer Georges Lemaitre first proposed it as a working hypothesis. However, it was not truly actively applied in cosmology until the mid-1960s, when two young radio astronomers accidentally made a remarkable discovery. The cosmology of the Big Bang, or more precisely, the expanding universe, had been developing since 1917, when Belinda Sitar found a solution to Einstein's equations describing the expansion of empty space. Alexander Friedmann found a solution in 1922, indicating that a universe filled with matter must either expand or contract. Edwin Hubble independently discovered the recession of galaxies in 1929. George Gamow realized in 1946 that the expanding universe must have been hot in the past. But it was only after the discovery by Penzias and Wilson that the Big Bang cosmology gained widespread acceptance among cosmologists. So, the two young radio astronomers accidentally made a remarkable discovery. They were Arno Penzias and Robert Wilson. In 1965, they were trying to use a large communication antenna in Holmdel, New Jersey, owned by Bell Labs. However, their work was hampered by continuous background noise, a constant hissing that made experiments impossible. The noise was persistent and uniform, coming from every direction, day and night, at any time of the year. For an entire year, the young astronomers did everything they could to find the source of the noise and eliminate it. They tested every electrical circuit, checked the equipment, pored over the circuits, twisted wires, and cleaned contacts. They climbed onto the antenna dish and taped every seam, every rivet. They returned with brooms and stiff brushes and cleaned thoroughly. As they later wrote in a scientific paper, the white dielectric substance commonly known as bird droppings did not help at all. They were unaware that just 50 kilometers away at Princeton University, a group of scientists led by Robert Dicke was struggling to find exactly what they were so diligently trying to eliminate. The Princeton researchers were developing ideas proposed in the 1940s by astrophysicist George Gamow, a native of Russia, that if one looked deep enough into space, one could detect some cosmic background radiation left over from the Big Bang. Gamow calculated that by the time this radiation crossed the cosmic expanses and reached Earth, it would manifest as microwaves. A little later, he even proposed a tool that could register them, the Bell Labs antenna in Holmdel. Unfortunately, neither Penzias nor Wilson, nor anyone from the Princeton group, had read Gamow's paper. The noise that Penzias and Wilson heard was, of course, the noise that Gamow had theoretically predicted. They discovered the edge of the universe, or at least its visible part, at a distance of more than 100 billion trillion kilometers. They saw the first photons, the ancient light of the universe. Although time and distance transformed them, as Gamow had predicted, into microwaves. Photons had been in the universe before, but they could not penetrate through the hot, dense matter, constantly being absorbed and re-emitted. Only about 300,000 years after the Big Bang did the universe cool enough for the photons to fly freely through space for billions of years until they were captured by terrestrial detectors. The expanding universe analogy helps to put this discovery into perspective. If you consider that you are peering into the depths of the universe, looking down from the 100th floor of the Empire State Building, where the 100th floor corresponds to our time, and the street level corresponds to the moment of the Big Bang. Then at the time of Wilson and Penzias's discovery, the most distant galaxies were found around the 60th floor, while the farthest objects, quasars, were somewhere around the 20th. The discovery by Penzias and Wilson brought our acquaintance with the visible universe to a height of half an inch above the basement floor. Still unaware of the source of the noise, Wilson, spinning himself, called Dickey at Princeton and described his problem to him, hoping he would suggest a solution. Dickey immediately understood what these two young men had discovered. "Yes, guys, we've been outdone," he told his colleagues. "Hang up." Soon, the Astrophysical Journal published two articles, one by Penzias and Wilson, describing their experience with the hissing detection, and the other by Dickey's group, explaining its nature. Although Penzias and Wilson were not searching for cosmic background radiation and did not know what it was when they discovered it, and did not explain its nature in their article in 1978, they received the Nobel Prize in Physics. The Princeton researchers received only sympathy. According to Denisov and Verby, authors of the book Lonely Hearts in Space, Penzias and Wilson did not fully understand the significance of what they had discovered until they read about it in the New York Times. By the way, the noise from cosmic background radiation is something we all know from experience. Tune your television to any channel with no transmission, and about 1% of the jumping electrostatic noise you see on the screen will be related to these ancient traces of the Big Bang. The next time you complain that there is nothing on the screen, remember that you always have the opportunity to witness the birth of the universe. Although everyone calls it the Big Bang, many books caution us against imagining it as an explosion in the ordinary sense. It was more of a sudden, significant expansion of colossal proportions. So what caused it? One point of view is that the singularity was a relic of an earlier scalar observation of the universe, that our universe is merely one of the eternal cycle of expanding and contracting universes, like a pneumatic chamber of an oxygen apparatus. Others explain the Big Bang as a so-called false vacuum, scalar field, or vacuum energy, a property or essence that somehow introduced a certain instability into the state of non-existence. It seems impossible to get something from nothing, but the fact is that there was once nothing, and now there is a universe, and this serves as evident proof of such possibilities. Perhaps our universe is merely part of a multitude of larger universes existing in different dimensions, and Big Bangs happen constantly and everywhere. Or perhaps space and time had completely different forms before the Big Bang, too alien to our understanding, and the Big Bang is a kind of transitional stage when the universe shifts from an incomprehensible form to one that we can almost understand. All of this is very close to religious questions. Cosmologist André Linde told respondents of the New York Times in 2001. The Big Bang theory is not about the explosion itself, but about what happened after the explosion, mainly shortly after the explosion. After making a plethora of calculations and careful observations at particle accelerators, scientists believe they can look back in time to just 10 to the minus 43rd second after creation, when the universe was still so small that it could only be viewed under a microscope. We should not faint at every unusual number we encounter, but perhaps from time to time it is worth grasping one of them, if only to remind ourselves of their incomprehensible and astonishing values. For instance, 10 to the minus 43rd is 1/10,000,000th of a trillionth of a trillionth of a second. Most of what we know, or think we know, about the early moments of the universe stems from concepts known as inflationary theory, which was first proposed for discussion in 1979 by particle physicist Alan Guth, who is now working at the Massachusetts Institute of Technology. He was 32 years old at the time and, by his own admission, had never seriously engaged in anything like it before. He might never have proposed his remarkable theory had he not accidentally attended a lecture on the Big Bang given by none other than Robert Dicke. The lecture sparked Guth's interest in cosmology, particularly regarding the question of the birth of the universe. Thus, the inflationary theory emerged, according to which the universe underwent a sudden and mind-boggling expansion. It inflated, effectively racing away from itself, doubling in size every 10 to the minus 34 seconds. The entire episode possibly lasted more than 10 to the minus 30th second, 1/1,000,000th of a millionth of a millionth of a second. It turned the universe, which would fit in your hand, into something at least 10 million billion million billion times larger. And the inflation theory explains the emergence of ripples and vortices in the universe that made it the way we know it. Without them, clumps of matter would not have formed, and thus no stars, leaving only gas and eternal darkness. According to Guth's theory, gravity arose in 1/10,000,000th of a trillionth of a trillionth of a second, and shortly thereafter, electromagnetism, as well as the strong and weak nuclear interactions, the main toys of physicists, joined in. A moment later, clusters of elementary particles, toys of these toys, were added. Suddenly, out of nothing, clouds of photons, protons, electrons, neutrons, and many other particles emerged in quantities ranging from about 10 to the 79th to 10 to the 80th of each type. This is roughly how the widely accepted theory of the Big Bang describes it. It is, of course, impossible to conceive such vast numbers. It is enough to know that in one noisy moment we were gifted with such a vast universe, no less than 100 billion light-years in diameter, according to the theory, although much larger sizes are possible, even infinite. And this universe is perfectly suited for the creation of stars, galaxies, and other complex systems. What is astonishing, from our perspective, is how fortunate it all turned out for us. If the universe had seemed a little different, if gravity had been slightly stronger or weaker, if processes had occurred a little slower or faster, then perhaps there would be no stable elements from which we are made, and no earth for us to walk upon. If gravity were a bit stronger, the universe would collapse in on itself like a poorly pitched tent, never reaching the proper density and composition. But if gravity were weaker, there would be no condensation of matter, and the universe would forever remain a dull, dispersed void. This is one of the reasons why some experts believe there may be many other Big Bangs, possibly trillions and trillions, scattered across the vastness of eternity, and we exist in this particular universe because we can only exist here. As Edward Ryan of Columbia University once noted in response to the question of why this happened, I offer a modest consideration that our universe is simply one of those that occasionally appear. He adds that although the birth of the universe may be extremely unlikely, he emphasizes that no one has counted the failed attempts. British astronomer Martin Rees believes that there are many, possibly an infinite number of universes, all with different properties in various combinations, and that we simply live in one of them where things combine in a way that allows us to exist. He draws an analogy with a very large clothing store. If there is a wide selection, you would not be surprised to find a suitable suit. If there are many universes, each governed by its own set of parameters, then among them, there will be at least one where a particular set of parameters conducive to life has been realized. We are in such a universe. Rees asserts that there are 6 quantities that broadly define the properties of our universe, and if any of these values were to change even slightly, things would not be as they are now. For example, for the existence of the universe as we know it, hydrogen must convert to helium in a strictly defined and quite leisurely manner, specifically with 7/1000ths of its mass converting to energy. Slightly decrease this value, say, from 7/1000ths to 6/1000ths, and the conversion will not occur. The universe would contain only hydrogen and nothing more. Slightly increase it to 8/1000ths, and the reactions would proceed so violently that hydrogen would have run out long ago. In both cases, the slightest change in the values of this universe that we know and need simply would not exist. It should be noted that everything is going as it should for now, but in the long term, gravity may turn out to be slightly stronger than necessary. One day, it may stop the expansion of the universe and force it to contract until it returns to singularity, possibly to start the whole process over again. On the other hand, gravity might be too weak, and in that case, the universe will expand forever until everything is so far apart that there will be no possibility for matter to interact, and the universe will become a very spacious but inert and lifeless place. The third possibility is that gravity seems perfectly tuned. Cosmologists have a term for this: critical density. In this case, gravity will hold the universe at just the right size to allow the established order of things to continue indefinitely. This is not the case. In the case of critical density, the universe will also expand infinitely and eventually become empty. But this will happen more slowly than in models with weak gravity. A statistical model of the universe that would stop expanding and not start contracting is not implied by Big Bang cosmology. Cosmologists sometimes refer to bright moments as fine-tuning of parameters, implying that everything is just right. These 3 possible universes are known as closed, open, and flat, respectively. And now, the question that has arisen in each of us at some point: what will happen if we reach the edge of the universe, so to speak, stick our head beyond the curtain? Where will the head be if it is no longer in the universe? What will we see beyond its limits? The answer is unappealing. You will never reach the edge of the universe, not even because it would take too long to get there, although that is certainly true, but because if you were to move further and further in a straight line, stubbornly and infinitely long, you would still never reach the outer boundary. Instead, you would return to where you started. At this point, you might feel disheartened and abandon the idea. This is explained by the fact that the universe bends in such a way that it cannot be properly visualized. According to Einstein's theory of relativity, and we will talk about that in due time. For now, it is enough to know that we are not floating in some enormous, expanding bubble. Space is curved in such a way that it remains boundless, but finite. Finiteness means that the volume of the universe can be expressed by some specific number, albeit a very large one. This is only possible in a closed model of the universe. In open and flat models, the volume of the universe is infinite, and in neither case does the universe have an edge or boundary. In space, it is strictly incorrect even to assert that space is expanding because, as Nobel laureate physicist Steven Weinberg notes, the solar system and galaxies are not expanding, and space itself is not expanding. Galaxies are rather receding from each other. All of this challenges intuition, or, as the renowned biologist J.B.S. Haldane once wonderfully noted, the universe is not only stranger than we suppose, it is stranger than we can suppose. To explain the curvature of space, the following analogies are usually presented. Try to imagine a resident of a universe of flat surfaces who has never seen a sphere and has arrived on Earth. No matter how far he wanders across the surface of the planet, he would never discover an edge. Eventually, he would return to the place where he started, utterly bewildered. In relation to the cosmos, we find ourselves in the same position as our puzzled flatlander, only we are confused by a greater number of dimensions. Just as there is no place where one can find the edge of the universe, there is also no center from which one can stand and say, "This is where everything began. This is the very center of all that exists." We are all at the center of it all, although in reality, we do not know this for sure and cannot prove it mathematically. Scientists simply assume that we cannot be at the center of the universe. Just imagine what that would mean. And so, phenomena must be the same for all observers in all places. And yet, precisely, we do not know this. For us, the universe extends to a distance covered by light over billions of years since its formation. This is the visible universe. The universe we know and can talk about has a diameter of about 1 million kilometers, 10 to the 24th power. But according to most theories, the universe as a whole, the meta-universe, as I sometimes call it, is even much more spacious. Rees believes that the number of light years in the circumference of this vast visible universe is expressed not by 10 zeros, not even by 100 zeros, but by millions. The space is much larger than you can imagine, without burdening yourself with attempts to reach something even more otherworldly. For a long time, the Big Bang Theory had one glaring gap that troubled many people. Namely, it could not explain how we got here. Although 98% of existing matter was created by the Big Bang, this matter consisted exclusively of light gases, helium, hydrogen, and lithium, as we have already mentioned. Not a single particle of heavy elements so essential for our existence, carbon, nitrogen, oxygen, and all the others, was produced from the gas furnace of creation. However, this presents a difficulty. To forge these heavy elements, heat and energy comparable to the Big Bang itself are required. But there was only one Big Bang, and it did not produce these elements. So where did they come from? Interestingly, the person who found the answer to this question was a cosmologist who deeply despised the Big Bang Theory, and it was he who coined the term in mockery of it. We will talk more about him soon, but before we return to the question of how we got here, it would be good to take a few minutes to ponder exactly where this here is. Nowadays, astronomers can do the most astonishing things. If someone were to strike a match, they could detect that flash through the most minute pulsations of distant stars. They can draw conclusions about the sizes, properties, and even potential habitability of planets too distant to be seen, so far away that it would take 500,000 years to reach them in an interplanetary ship. With their radio telescopes, they can capture radiation so weak that the total amount of energy received from beyond the solar system since radio observations began in 1951, across all instruments combined, amounts to, according to Carl Sagan, an American astronomer, less than the energy of a single snowflake falling to Earth. In short, there is not much happening in the universe that astronomers could not detect if they wished. It is all the more surprising that until 1978, no one had noticed that Pluto had a moon. In the summer of that year, young astronomer James Christie from the United States Naval Observatory in Holmdel, Arizona, while examining photographic images of Pluto, suddenly noticed that there was something else there, something blurred, unclear, but definite, and not just Pluto itself. After consulting with colleague Robert Harrington, he concluded that it was a moon, and not just any moon, but relative to its planet, it was the largest moon in the solar system. In fact, this was somewhat of a blow to Pluto's status as a planet, a status that had never been particularly solid, as the place occupied by the moon and the place occupied by Pluto had previously been considered one whole. Now it meant that Pluto was much smaller than previously thought, even smaller than Mercury. Moreover, there are 7 moons in the solar system, including our moon, that surpass Pluto in size. Naturally, the question arises, why was this moon not found in our own solar system for so long? The answer is partly related to where astronomers aim their instruments, partly to the purposes for which they are designed, partly to the peculiarities of Pluto itself, but mainly to where the instruments are directed. According to astronomer Clark Chapman, most people think that astronomers come to observatories at night and gaze at the sky. This is not the case. Almost all telescopes in the world are designed to peer into tiny sections of the sky to see distant quasars or hunt for black holes, or to closely examine distant galaxies. The only existing network of telescopes scanning the sky was designed and built by the military. In fact, many observatories work on compiling so-called sky surveys in various ranges of radiation. Usually, special telescopes are built for this purpose, which systematically photograph the entire available and observable sky, square by square. In the past, such surveys typically took many months, sometimes even years. Recently, networks of wide-angle robotic telescopes have been rapidly developing, which will soon be able to survey the entire night sky in just a few days. We are spoiled by artists' renderings and imagine the clarity and resolution of images to be such as they are not actually found in astronomy. Pluto in a photograph looks dim, blurred, like a piece of cosmic cotton, and its moon does not resemble the romantically illuminated, sharply defined sphere you would see in a National Geographic illustration. Rather, it is a barely noticeable vague hint of yet another murky spot. It was so indistinct that it took another 7 years for someone to find the moon again, and thereby independently confirm its existence. Interestingly, Christie made his discovery in Holmdel, as it was here in 1930 that Pluto itself was first discovered. This significant event in astronomy is largely credited to astronomer Percival Lowell, who came from one of the oldest and wealthiest Boston families, the very one referred to in the famous song that Boston is the home of beans and oddballs, where Lowell conversed only with hooves and with God, only with God. He financed the creation of the famous observatory bearing his name. But he left the most indelible mark on history with his hypothesis that Mars was covered with canals built by industrious Martians to transport water from the polar regions to the dry but fertile lands closer to the equator. Lowell actively conducted observations at his observatory, although the canals on Mars were not discovered by him, but by Italian astronomer Giovanni Schiaparelli. It was Lowell who firmly associated them with fantastic Martians. However, not only were Martians not found, but neither were the canals. Lowell's second firm belief was that there must exist an undiscovered ninth planet beyond Neptune, which he referred to as Planet X. In his conviction, Lowell based his ideas on the discrepancies he found in the orbits of Uranus and Neptune, dedicating the last years of his life to attempts to locate the gas giant he was sure was out there. Unfortunately, in 1916, Lowell passed away unexpectedly, partly due to health issues exacerbated by his relentless search. The search was halted, and Lowell's heirs quarreled over his estate. However, in 1929, partly to divert attention from the saga of Martian canals, which had seriously tarnished the observatory's reputation by that time, the administration of the Lowell Observatory decided to resume the search and hired a young astronomer from Kansas, Clyde Tombaugh. Tombaugh did not have formal astronomical education, but was known for his diligence and cleverness. After a year of patient searching, he finally managed to discover Pluto, a barely visible bright dot among the sparkling array of stars. This was an astonishing find, particularly given that Lowell's conception of a new planet beyond Neptune turned out to be completely erroneous. Tombaugh immediately recognized that the new planet was nothing like the enormous gas sphere Lowell had described, but all caveats regarding the nature of the new planet, whether voiced by Tombaugh himself or others, were quickly dismissed in the sensational frenzy that accompanied any significant news. This was the first planet discovered by Americans, and no one wanted to consider that, in reality, it was merely a distant ice ball. It was named Pluto, partly because the first two letters formed an acronym of Lowell's initials. Lowell was posthumously celebrated as a great genius everywhere, though he was nearly forgotten, remembered only among astronomers studying planets who held him in deep respect. Some astronomers still believe that there may be a Planet X out there, a true giant, possibly 10 times the size of Jupiter. But it is so far away that it remains invisible for now. It would receive so little sunlight that it would have almost nothing to reflect. There is speculation that it could be an unusual planet like Jupiter and Saturn, but it is located too far away. Rumors suggest distances of around 7 trillion kilometers. More likely, it resembles an unfinished monsoon. Most star systems in the cosmos are binary, consisting of 2 stars, which makes our solitary sun somewhat peculiar. Pluto's dimensions are now fairly well defined. Its diameter is 2,306 plus or minus 20 kilometers. Many astronomers consider it not a planet at all, but merely the largest object discovered so far in the region of cosmic debris known as the Kuiper Belt. In 2005, a group of astronomers led by Michael Brown discovered an object in the Kuiper Belt, provisionally designated 2003 and 113, which exceeds Pluto in size. This discovery further intensified the debate over Pluto's status, and ultimately, after lengthy discussions, led to the revocation of its planet status. This occurred on August 24, 2006. In fact, the Kuiper belt was theoretically predicted in 1930 by astronomer Leonard, but it is named after the Dutchman Gerard Kuiper, who worked in America and developed the idea. The Kuiper belt serves as the source of so-called short-period comets, those that appear relatively regularly. The most famous among them is Halley's comet, which leads a more solitary existence. Long-period comets among them. Recent visitors like Hale-Bopp and Hyakutake emerge from the much more distant Oort Cloud. Undoubtedly, Pluto behaves quite differently from other planets. Pluto's orbit is well defined, and astronomers can easily calculate its movement thousands of years into the past and future. While the orbits of other planets lie more or less in the same plane, Pluto's orbit is tilted at 17 degrees, akin to a dandy's hat tilted askew. Its orbit is so unusual that at each turn of its solitary journey around the Sun, it is noticeably closer to us than Neptune. For most of the 1980s and 90s, Neptune was the most distant planet in the solar system. It was not until February 11th, 1999, that Pluto returned to the outer row, where it will now spend 228 years. So even if Pluto is indeed a planet, it is certainly a very strange, tiny one. Its mass is only 0.25% of Earth's mass. If you place Pluto on the territory of the United States, it would not occupy even half the area of the 48 contiguous states. This alone is a significant anomaly. Thus, our planetary system consists of 4 inner terrestrial planets, 4 outer gas giants, and a tiny solitary ice ball. However, there is every reason to believe that in that region of space, we will soon begin to find other, even larger ice balls, and then we will face challenges. After Christie discovered Pluto's moon, astronomers began to scrutinize this sector of space more actively, and in early December 2002, they found more than 600 Trans-Neptunian objects, or the Webb, as they are sometimes called. The term Webb has not caught on. Currently, the International Astronomical Union has recommended using the term dwarf planet for spherical objects that do not qualify as planets and small solar system bodies for all other objects. One of those from the Webb, named Eris, is nearly the same size as Pluto's moon. Astronomers now believe that the number of such objects could be in the billions. The difficulty lies in the fact that many of them are extremely dark. Their albedo, or reflective capability, is typically only 4%, roughly like a piece of charcoal. Moreover, these chunks of charcoal are over 6 billion kilometers away from us, and how far that truly is, it's almost beyond imagination. You see, space is simply vast, if not monstrous. To grasp this, and just for fun, imagine we are about to embark on a journey in a rocket ship. We will not travel very far, just to the edge of our solar system, simply to determine how vast the cosmos is and what a tiny part of it we occupy. Now for the bad news. I'm afraid we won't be home in time for dinner. Even at the speed of light, 300,000 kilometers per second, it would take 7 hours to reach Pluto, depending on its position in orbit. Light takes anywhere from 4 to 7 hours to reach it. Currently, this journey takes about 5.5 hours, but of course, we cannot travel at that speed. We will have to fly at the speed of an interplanetary spacecraft, which is much slower. The highest speed achieved by human-made objects is that of the Voyager 1 and Voyager 2 spacecraft, which are currently moving away from us at 50,000 kilometers per hour. Voyager 1 is moving relative to the Sun at a speed of over 61,200 kilometers per hour, 17 kilometers per second. Voyager 2's speed is 5,800 kilometers, or 1.6 kilometers per second slower. The reason for launching the Voyagers at that specific time, August and September 1977, was that Jupiter, Saturn, Uranus, and Neptune aligned in a way that occurs only once every 175 years. This allowed Voyager to utilize gravitational assist techniques, where the spacecraft sequentially flies from one gas giant to another, as if propelled by a cosmic whip. But even so, it took them 9 years to reach Uranus and 12 years to cross Pluto's orbit. So, the first thing you probably grasped is that space is aptly named. One of the meanings of the English word space is empty place, and it is terribly lacking in events. Our solar system is perhaps the most vibrant place for trillions of miles around, yet everything we see in it, the sun, planets with their moons, a billion or so tumbling rocks, the asteroid belt, comets, and various other floating debris, occupies less than 1/1,000,000th of the available space. You can also easily understand that on none of the maps of the solar system you have encountered does the scale even remotely correspond to reality. On most school diagrams, the planets are depicted side by side, tightly next to one another. In many illustrations, the giant planets even cast shadows on each other, but this is an inevitable deception to fit them all on one sheet of paper. In reality, Neptune is not just a little behind Jupiter. It is far behind, 5 times farther than Jupiter is from us, so far that it receives only 3% of the sunlight that Jupiter gets. These distances are such that it is practically impossible to depict the solar system to scale. Even if you made textbooks with large fold-out inserts or simply took the longest sheet of paper for signs, it still would not be enough. If in a scaled diagram of the solar system, Earth is represented as the size of a pea, Jupiter would be 300 meters away, and Pluto would be 2.5 kilometers away and the size of a bacterium. So in any case, you would not be able to see it. This is an exaggeration. Pluto is only 5.5 times smaller than Earth. On a sand scale, it would be about the size of a millimeter. On that same scale, the nearest star, Proxima Centauri, would be 16,000 kilometers away from us. Even if you managed to get everything to the point where Jupiter became the size of a dot at the end of this sentence, and Pluto no bigger than a molecule, even then, Pluto would be over 10 kilometers away. On this scale, Pluto's size would be about 5 microns. That's the size of a large bacterium, which is thousands of times larger than the size of molecules. So the solar system is indeed vast. When we reach Pluto, we will be so far away that the sun, our native, warm, life-giving sun, will shrink to the size of a pinhead, a bit larger than a bright star. In reality, the sun on Pluto is significantly brighter than a full moon on Earth. You could easily read by its light. In such a soul-crushing emptiness, you will begin to understand why even quite significant objects, like Pluto's moon, have eluded attention. In this sense, Pluto is not alone. Before the Voyager flew by, it was thought that Neptune had 2 moons. Voyager found 6 more. When I was a boy, it was believed that there were 30 moons in the solar system. Now, there are at least 90. About a third of them have been discovered in the last 10 years. This suggests that when we judge the universe as a whole, we must remember that we essentially do not know what is happening in our own solar system. And now one more thing to consider. As we fly past Pluto, we are merely flying past Pluto. If you look at the flight plan, you will see that its destination is the edge of the solar system. But I'm afraid we have not yet reached it. Pluto may be the last object marked on school diagrams, but the system itself does not end here. In fact, its end is not even in sight. We will not reach the edge of the solar system until we pass through the Oort Cloud, a vast realm of wandering comets. And we will not reach the Oort Cloud any sooner than, in 10,000 years. Pluto accounts for only 1/50th of the distance, but it is not the end of the solar system, as is so bluntly indicated on school diagrams. Note: since the Oort Cloud remains a hypothetical object, astronomers generally tend to consider the boundaries of the solar system to be the so-called heliopause, an area where the solar wind, a stream of charged particles emitted by the sun, collides with the interstellar medium and mixes with it. The distance to the heliopause is roughly twice as far as to Pluto, and the interplanetary probe Voyager 1 began crossing the heliopause in mid-2012. We certainly have no chance of making such a journey. Even a trip of 386,000 kilometers to the moon is still quite a complex undertaking. The flight of humans to Mars, which President Bush briefly called for in a moment of dizziness, has quietly been put aside after someone calculated that it would cost $450 billion and might end with the destruction of the entire crew. Their DNA would be shredded by high-energy solar particles from which they could not protect themselves. Based on what we now know, we can imagine, within reason, that there is absolutely no chance that humans will ever reach the edge of the solar system. It is simply too far. Under current conditions, even with the Hubble Space Telescope, the Oort Cloud cannot be seen, so we essentially do not know what is out there. Its existence is quite probable, but remains a hypothesis. It would be more accurate to refer to it as the Oort Cloud. The Estonian astronomer Ernst Oort proposed this hypothesis in 1932, and the Dutch astronomer Jan Oort refined the calculation 18 years later. All we can confidently say about the Oort Cloud is that it begins somewhere beyond Pluto and stretches approximately 2 light-years into space. The primary unit of length in the solar system is the astronomical unit, denoted as AU, which corresponds to the distance from the Sun to the Earth. Pluto is about 40 AU away from us, while the core of the Oort Cloud is approximately 50,000 AU. In other words, quite a distance. But let's imagine again that we have reached the Oort Cloud. The first thing you will notice is that there is complete tranquility here. We have ventured very far, so far that even our sun is not the brightest star in the sky. It is astonishing that such a tiny distant point of light has enough gravitational strength to hold all these comets in orbit. These bonds are not very strong, so the comets drift majestically at speeds of only a few hundred kilometers per hour. From time to time, one of these lonely comets is nudged from its usual orbit by some weak gravitational disturbance, possibly from a passing star. Sometimes they are ejected into the emptiness of space, and we will never see them again. But occasionally, they transition to an elongated orbit around the Sun. Every year, 34 such long-period comets pass through the inner regions of the solar system. Occasionally, these random visitors collide with something solid, like Earth. So why are we here? The comet we arrived on has just begun its long descent toward the center of the solar system. It is heading, believe it or not, toward the town of Manson in the state of Maine. It will take it a long time to get here, at least 3 to 4 million years. So let's leave it alone and return to it later. So this is our solar system. And what lies beyond the solar system? Nothing, and yet so much. It depends on how you look at it. In the short term, there is nothing. The deepest vacuum ever created by humans is not as empty as interstellar space, and you will have to traverse a considerable amount of this nothing before you reach the next piece of something. Our nearest cosmic neighbor, Proxima Centauri, part of a triple star system known as Alpha Centauri, is 4.3 light-years away from us. A trifle by galactic standards, yet it is 100 million times farther than the Moon. To reach it, an interplanetary spacecraft would take at least 25,000 years. Even if you made that journey, you would still find nothing but a lonely cluster of stars amid boundless emptiness. To reach the next notable landmark, Sirius, you would need to cover another 4.6 light-years. Strictly speaking, Sirius is the sixth closest star system to the Sun. It consists of 8 stars, but the only closer stars, besides Alpha Centauri, are not visible to the naked eye. The distance from the Sun to Sirius is 8.6 light-years, while from Proxima Centauri to Sirius is even farther, 9.3 light-years, as these stars are in different directions from the Sun. And it will continue to be that way. If you want to wander through space from star to star, just to reach the center of our galaxy would take longer than the existence of humankind. The cosmos, let me reiterate, is something monstrously vast. The average distances between stars exceed 30 million kilometers. Even at speeds approaching the speed of light, this is fantastically far for any wandering individual. Of course, it is possible that extraterrestrial beings traverse billions of miles for fun, making crop circles in Wiltshire fields, or scaring poor guys driving pickup trucks down deserted roads somewhere in Arizona. After all, they must have mischievous teenagers, but this still seems extremely unlikely. Statistically, the likelihood that there are thinking beings out there is quite decent. No one knows exactly how many stars are in the Milky Way. Estimates range from 100 billion to possibly 400 billion, and the Milky Way is just one of 140 billion galaxies, many of which are even larger than ours. The number of galaxies in the observable universe is even less precisely known, but there is reason to believe that there are over 1 trillion. In the 1960s, Cornell University professor Frank Drake, excited by such monstrous figures, devised a famous formula for calculating the probability of advanced life existing in the cosmos as a series of multiplicative probabilities. According to Drake's formula, you multiply the number of stars in a selected region of the universe by the fraction of stars that may have planetary systems, then multiply that by the fraction of planetary systems theoretically capable of supporting life. Multiply by the fraction of those where life arises and produces intelligence, and so on. With each of these multiplications, the numbers shrink dramatically, but even with the most conservative starting figures, the number of advanced civilizations in just the Milky Way is invariably in the millions. Experts strongly disagree on the values that go into Drake's formula. Some indeed arrive at millions of civilizations in the galaxy, while others conclude that our civilization is hardly the only one. There is currently insufficient scientific data to resolve this dispute. It is such an interesting, thrilling thought. We may be just one of millions of advanced civilizations. Unfortunately, the cosmic space is so vast that the average distance between any two of these civilizations is estimated to be at least 200 light years. Easier said than imagined. To start with, even if these beings know about us and are somehow able to observe us through their telescopes, they are seeing light that left Earth 200 years ago. So they are not seeing you and me. They are witnessing the French Revolution, Thomas Jefferson, people in silk stockings and powdered wigs, folks who do not know what an atom or a gene is, generating electricity by rubbing an amber stick with a piece of fur and thinking that is quite a clever trick. Any message we might receive from these observers will likely begin with the salutation, "Dear Sir," and contain congratulations on our horses and skillful exploitation of whale oil. 200 light years is so far for us that quite simply it is beyond our understanding. So even if we are not alone, in principle, in practice, we remain alone. Carl Sagan estimated that there are about 10 billion trillion suitable planets in the universe, a number that is mind-boggling. But what is utterly unimaginable is the sizes of the spaces in which they are scattered. If I were to randomly throw something into space, Sagan writes, the chances of landing on the surface of a planet or near it would not exceed 1 in a billion trillion trillion. That means 10 to the 33rd power, or 1 with 33 zeros. That is why, perhaps, the good news is the official recognition in February 1999 of Pluto as a planet by the International Astronomical Union. The universe is vast and a desolate place. We would be satisfied with any neighbor. In 2006, the discussion about Pluto's status took an opposite turn. Most astronomers had long recognized that Pluto is fundamentally no different from other objects in the Kuiper Belt. For the last few decades, its status as a planet was maintained solely by tradition. The International Astronomical Union, responsible for the nomenclature of celestial objects, twice appointed committees to develop a formal definition of a planet. Astronomers sought, on one hand, to provide a physically grounded definition, while on the other, to preserve the tradition that recognized Pluto as a planet. However, both committees failed to accomplish this task, and ultimately, at the 26th General Assembly, a definition was adopted stating that Pluto is not a planet. Along with a few other objects in the Kuiper Belt and the asteroid series, it has now been classified as a dwarf planet. When the sky is clear, the moon not too bright, Reverend Robert Evans, a calm and unflappable man, hauls a bulky telescope out to the back porch of his home in the Blue Mountains of Australia, about 80 kilometers from Sydney, and engages in his usual pastime. He gazes into the depths of the past and finds dying stars. Gazing into the past is, of course, the easiest part of the job. Look at the night sky, and a history unfolds before you, a multitude of stories. Not the stars as they are now, but as they were when the light that has reached us departed. How can we know if our faithful companion, the North Star, is still intact, whether it burned out completely last January, or in 1854, or at any time since the early 14th century, and simply that news has not yet reached us? The most we can always assert is that it still shone 680 years ago on that day. Stars die all the time. What Bob Evans does better than anyone who has tried this is to catch the moments of stellar farewells. Evans, a good-natured and now almost retired minister of the Uniting Church in Australia, sometimes substitutes for a soup kitchen and is a scholar studying the religious achievements of the 19th century. But at night, he transforms into a modest titan of the heavens. He hunts for supernovae. A supernova occurs when some giant star, much larger than our sun, collapses and then spectacularly explodes, releasing energy equivalent to hundreds of billions of suns and burning brighter than all the stars in its galaxy combined for a time. It is like the simultaneous explosion of 1 trillion hydrogen bombs, says Evans. According to him, if a supernova were to explode in our corner of the cosmos, it would be the end for us. It would ruin the whole show, the astronomer cheerfully concludes. But the universe is boundless. Supernovae are usually too far away to cause us harm. In fact, most of them are so unimaginably distant that the light from them reaches us only as a barely noticeable flicker. For about a month, while they are visible, they differ from other stars only in that they occupy a spot in the sky that was not filled before. And it is these anomalous, very rarely appearing tiny dots that Reverend Evans seeks out in the full starry night sky. To understand what a skill this is, imagine a regular dining table covered with a black tablecloth, with a handful of salt scattered across it. The scattered grains of salt can be taken for a galaxy. Now imagine 1,500 such tables, enough to line them up in a row 3 kilometers long, and randomly sprinkle salt on each. Add a grain of salt to one of these tables and let Bob Evans walk along. He will find it at first glance. That grain is the supernova. In fact, the brightness of a supernova is comparable to that of a galaxy, so it is more accurate to speak not of one added grain, but of a handful that has been scattered on the table. Evans possesses such exceptional talent that Oliver Sacks mentions him in his book, An Anthropologist on Mars, in a chapter dedicated to autism, immediately adding, "There are no signs that he suffers from autism." Evans, who has never met Sacks, laughs at the suggestions that he is a scientist or suffers from autism, but cannot explain where this talent comes from. "I simply have the ability to remember star fields." The term supernova was coined in the 1930s by the memorable astrophysicist Fritz Zwicky, who was born in Bulgaria and grew up in Switzerland. Zwicky came to the California Institute of Technology in the 1920s and immediately stood out for his eccentricities and unbearable character. It cannot be said that he possessed brilliant abilities, and many colleagues regarded him as an annoying clown. A passionate advocate of a healthy lifestyle, he often dropped to the floor in Caltech's cafeteria or elsewhere in public and did push-ups on one hand, demonstrating his strength to anyone who might doubt him. He was a provocative troublemaker, and over time his behavior became so frightening that his closest colleague, Walter Baade, a very mild-mannered man, did not dare to be alone with him. Among other things, Zwicky accused Baade, a German by nationality, of being a Nazi, which he never was, and at least once threatened to kill Baade, who was working at the observatory on Mount Wilson, if he ever appeared on the Caltech campus. But despite all this, Zwicky was capable of the most astonishing and brilliant discoveries. In the early 1930s, he turned his attention to a question that had long troubled astronomers: the appearance of inexplicable bright points in the night sky, new stars. Incredibly, he asked himself whether it could be that a neutron, the subatomic particle just discovered in England by James Chadwick, was at the root of all this, and which was at that time a fashionable novelty. He had the insight that if a star collapses to a density comparable to that of an atomic nucleus, an unimaginably compact object would form. Atoms would literally crush each other, Their electrons would merge into neutrons in the core. A neutron star would result. Imagine 1,000,000 hefty cannonballs compressed to the size of a toy glass marble. And that is still not quite an accurate comparison. The core of a neutron star is so dense that a spoonful of its substance weighs 90 billion kilograms. One spoonful. But that's not all. Zwicky realized that during the collapse of such a star, an enormous amount of energy is released, enough to produce the greatest explosions in the universe. He named these explosions supernovae. They were to turn out to be the largest events in the cosmos. On January 15, 1934, a very brief summary appeared in the journal Physical Review, made the previous month at Stanford University, reporting Zwicky's and Bod's findings. Despite its extreme brevity, one paragraph spanning 24 lines, this summary contained an enormous amount of new scientific information. It included the first mentions of supernovae and neutron stars, convincingly explained the process of their formation, accurately assessed the force of the explosion, and, as an additional bonus, linked supernova explosions to a mysterious new phenomenon called cosmic rays, which had recently been discovered to literally swarm throughout the universe. These ideas were revolutionary, to say the least. Confirmation of the existence of neutron stars took 34 years to arrive. The hypothesis regarding cosmic rays, while considered plausible, has yet to be definitively confirmed. Overall, this summary, according to astrophysicist Kip Thorne from the California Institute of Technology, turned out to be one of the most prescient documents in the history of physics and astronomy. Interestingly, Friedrich Zwicky hardly understood why all these things should happen. According to Thorne, he did not grasp the laws of physics well enough to justify his ideas. Zwicky had the ability to propose grand ideas, while others were primarily left to provide the mathematical justification. He was also the first to realize that there was a severe lack of visible matter in the universe to hold galaxies together, and that there must be some other source of gravitational influence, what we now call dark matter. He only missed one thing. If a neutron star is compressed sufficiently, it becomes so dense that even light cannot escape its monstrous gravitational pull, resulting in a black hole. Unfortunately, most of his colleagues did not appreciate Zwicky, and his ideas went largely unnoticed. When, 5 years later, the great Robert Oppenheimer drew attention to neutron stars in an epoch-making paper, he did not mention Zwicky's work at all, even though he had been studying the same problem for years. In an office a little further down the hall, Zwicky's conclusions regarding dark matter did not attract serious attention. For nearly 40 years, one can only speculate about how many push-ups he completed during that time. Looking up at the sky, we see surprisingly little of the universe with the naked eye. From Earth, only 6,000 stars are visible, and only about 2,000 of them can be seen at once through binoculars. The number of stars visible from a single point increases to 5 to 10,000, and with a small 2-inch telescope, it jumps to 300,000. With a 16-inch telescope, like Evans's, the count shifts from stars to galaxies. Evans believes that from his porch, he can see between 50 and 100,000 galaxies, each containing billions of stars. This is certainly impressive, but supernovae remain an extremely rare phenomenon. A star may burn for billions of years, but it dies only once and very quickly, with only a few dying stars exploding. Most fade away, like a campfire at dawn. In a typical galaxy, which contains 100 billion stars, a supernova typically flares up once every 2 to 300 years. Therefore, searching for supernovae is akin to standing on the observation deck of the Empire State Building, peering through a telescope at the windows of Manhattan in the hope of spotting someone lighting candles on a birthday cake. So when a hopeful and courteous priest began asking whether there were suitable star charts for finding supernovae, the astronomical community considered him to be out of his mind. At that time, Evans had a 10-inch telescope, a fairly decent size for amateur stargazing, but hardly suitable for serious cosmology. With this instrument, he intended to discover one of the rarest phenomena in the universe. Throughout the history of astronomy, before Ivan began this endeavor in 1980, fewer than 60 supernovae had been found. In fact, by that time, more than 500 supernovae had already been discovered, and today, over 6,000 are recorded. When I visited him in August 2001, he had just recorded his 34th visual discovery, with the 35th following 3 months later, and the 36th at the beginning of 2003. According to the catalog of discovered supernovae, this was Evans's 40th discovery, with the first 16 supernovae he found not visually, but through photographs. He discovered his last supernova in March 2008, bringing his total to 48. Krivonos, however, had certain advantages. Most observers, like most people in general, are located in the northern hemisphere, so a significant portion of the sky was almost entirely at his disposal, at least initially. He also had speed and an astonishing memory on his side. Large telescopes are quite cumbersome, and a significant portion of their working time is spent aiming them at the desired object. Evans spins his small 16-inch telescope like a tail gunner in a dogfight, spending no more than a couple of seconds on any given patch of sky. As a result, in an evening, he could observe perhaps 400 galaxies, while a large professional telescope, if lucky, might survey 50 or 60. Searching for supernovae usually means not finding them. From 1980 to 1996, he averaged 2 discoveries per year. Not a great reward for 100 nights of intense stargazing. Once, he discovered 3 in 50 days, but at another time, it took 3 years before he found one. In the absence of discoveries, there is a certain benefit, he says. It helps cosmologists determine the rate of galaxy evolution. This is one of the rare areas where the mere absence of facts is itself a fact. If you've ever peeked into popular astronomical institutions, you must know that they are usually filled with bright, colorful images of distant nebulae or something similar, bathed in the magical light of heavenly clouds, majestically moving and shimmering with the subtlest hues. Evans's working images bear no resemblance to these. They are merely blurry black and white photographs with tiny dots surrounded by halos. This is a star from a constellation known as the Seal, in a galaxy astronomers refer to as, or JC 1365. JC stands for the New General Catalog, which lists galaxies. At that time, it was a hefty book on someone's desk in Dublin. Now, of course, it is a database, the light of which bears witness to the impressive demise of this star, relentlessly racing through space for 60 million years until one night in August 2001, it reached Earth as a flash of light, a tiny illumination in the night sky. And, of course, Robert Evans noticed it on his porch, which smelled of eucalyptus. It brings me special satisfaction Evans says, to think that light, traveling through space for millions of years, reaches Earth just as someone is looking at that particular patch of sky. It seems important that events of such magnitude are witnessed. The role of supernovae is not limited to evoking a sense of wonder and admiration. They are divided into several types, one of which, incidentally, was discovered by Evans, while another, known as Type 1a supernovae, is important for astronomy because these supernovae always explode in the same way, having the same critical mass. Therefore, they can be used as standard candles. By measuring their brightness, and thus their relative distance, we can determine the rate of expansion of the universe. In 1980, astrophysicists Saul Perlmutter and Adam Rees from the Sky Laboratory in Berkeley, California, needed more Type 1a supernovae than were provided by conventional visual observations, and they set out to find a more systematic method for their search. In 2011, Perlmutter was awarded the Nobel Prize in Physics for the discovery of the phenomenon of the accelerated expansion of the universe, made through observations of distant supernovae in 1999 and confirmed by numerous supernovae discovered later, as well as other observational data. Perlmutter developed a clever system using sophisticated computers and charge-coupled devices, essentially excellent digital cameras. This automated the search for supernovae. Telescopes can now take thousands of images, allowing computers to find the characteristic bright spots indicating supernova explosions. Until recently, not all supernovae could be automatically detected in digital images. Humans perform this task much better. A project called Hand-On was even launched, allowing school children to participate in the search for supernovae through images of galaxies. However, in recent years, the efficiency of automatic supernova recognition has significantly improved, and amateurs can no longer compete with networks of robotic telescopes. Over 5 years, using the new technology, Perlmutter and his colleagues discovered 42 supernovae in Berkeley. Now, even amateurs find supernovae using CCD matrices. Now, you can point a telescope at the sky and sit at home watching television, Evans said, with a hint of concern. It destroys all the romance of the pursuit. I asked him if he felt tempted to adopt the new technology. It liberates, he replied. I love working in my own way too much. Moreover, he nodded toward the images of his latest supernova and smiled. Sometimes I still manage to outsmart them. Scottish amateur astronomer Tom Bowles built an observatory with 3 robotic telescopes that constantly scan the sky for supernovae. In 2003 alone, he became the first to discover 300 supernovae, and he has a total of 148 exploded stars to his credit. This earned him the title of champion among amateurs for discovering supernovae, surpassing Robert Adams. Bowles continues to search for supernovae, although in recent years his discovery rate has somewhat decreased due to competition from professional laboratories. Naturally, a question arises. What would happen if a star exploded nearby? As we already know, our closest stellar neighbor, Alpha Centauri, is 4.3 light-years away from us. I imagine that if an explosion were to occur, we would have 4.3 years to watch the light from this majestic event spill across the sky, as if poured from a giant jug. What would it be like to have to observe a catastrophe approaching us for 4 years and 4 months, knowing exactly when it would happen? There would be nothing left for us. Would people still go to work? Would farmers still grow crops? Would anyone deliver them to the store? and the news of such an event travels at the speed of light. But so does the destructive force, so you would learn of it and perish at the same moment. But do not worry, because it will not happen. For a supernova wave to destroy you, he explained, you would need to be laughably close, say, within about 10 light years. The danger would come from various types of radiation, cosmic rays and the like. They would create stunning auroras, shimmering across the sky like a curtain of ghostly light. This would not bode well. Anything capable of creating such a spectacle could just as easily sweep away the magnetosphere, which lies high above Earth, a magnetic belt that normally protects us from ultraviolet rays and other cosmic radiation. However, in the event of a nearby supernova explosion, neither the atmosphere nor the magnetosphere would be able to protect us from the harsh radiation. The reason we can be more or less confident that such an event will not occur in our corner of the galaxy, Thorne says, is that a certain type of star is required for a supernova to happen in the first place. The candidate star must be 10 to 20 times more massive than our Sun, and there is nothing of the right size nearby. Fortunately, the universe is vast enough. The nearest possible candidate, he added, is Betelgeuse. Its possible outbursts and fluctuations over the years indicate that some interesting instabilities are taking place there. However, Betelgeuse is 500 light-years away from us. Only half a dozen times in documented history have supernovae flared up close enough to be visible to the naked eye. One of these explosions in 1554 led to the formation of the Crab Nebula. Another, in 1604, produced a star so bright that it was visible during the day for 3 weeks. The most recent was in 1987. At that time, a supernova ignited in a region of space known as the Large Magellanic Cloud, but it was barely visible only in the southern hemisphere and was at a perfectly safe distance of 169,000 light-years away. Supernovae are fundamentally important in another significant sense. Without them, we would not be here. The Big Bang led to the formation of light gases, but not heavy elements. The latter appeared later. For a long time, no one understood how this happened. The fact is that something truly hot, even hotter than the centers of the hottest stars, is required to forge carbon, iron, and other elements, without which we would be, to our great dismay, utterly defenseless. The explanation came in the form of supernovae, and it was an English cosmologist, much like Fritz Zwicky in his mannerisms, who figured this out. His name was Fred Hoyle, a Yorkshireman who passed away in 2001, as noted in his obituary in the journal Nature. He was referred to as a cosmologist and a dust spot, and he was indeed both. In the obituary, it was stated that he spent much of his life embroiled in controversies and signed off on all sorts of nonsense. For instance, he claimed without any evidence that the fossil Archaeopteryx, treasured in the Natural History Museum, was a forgery, much like Piltdown, a narrow hoax that infuriated museum paleontologists who had to fend off phone calls from reporters around the world for many days. Between 1908 and 1911, fragments of a skull and jaw were found near Piltdown in Sussex, England, which were long considered to belong to a creature intermediate between ape and human. However, in the 1950s, British museum staff conducted chemical analyses that showed the Piltdown samples were finely crafted forgeries. He also believed that not only life, but also many diseases, such as influenza and bubonic plague, were brought to Earth from space. Once, he suggested that during the process of evolution, humans developed a protruding nose with downward-facing nostrils to prevent cosmic pathogenic organisms from entering. But, in a playful mood, during a radio broadcast in 1952, he coined the term Big Bang. He noted that our physical concepts cannot explain why everything that exists, gathered in a point, should suddenly begin to expand. Hoyle preferred the steady-state theory, according to which the universe is constantly expanding and continuously creating new matter as it expands. He also understood that if a star collapses catastrophically, it releases an enormous amount of heat, heating up to 100 million degrees or more, which is enough to initiate the formation of heavy elements, a process known as nucleosynthesis. Nucleosynthesis encompasses all thermonuclear reactions leading to the formation of heavier element nuclei from lighter ones. Nucleosynthesis begins with the birth of the universe, continues throughout the life of a star, and during a supernova explosion, only a small amount of the heaviest elements, those heavier than iron, is synthesized, while the primary products of stellar nucleosynthesis are scattered into space, where they can become part of new, forming stars and planets. In 1957, working alongside other scientists, Hoyle demonstrated how heavy elements are formed during supernova explosions. For this work, one of his collaborators, William Alfred Fowler, received the Nobel Prize, while Hoyle, to our collective shame, did not. According to Hoyle's theory, an exploding star releases enough energy to create all new elements and scatter them into space, where they form gas clouds in the interstellar medium, which eventually condense into new solar systems. With the emergence of these theoretical formulations, it finally became possible to create a plausible scenario for our existence here. It is now believed that about 4.6 billion years ago, in the region of cosmic space where we currently reside, a massive whirlpool of gas and dust with a diameter of 24 billion kilometers began to form and collapse. Almost all of the 99.9% of the mass of the solar system went into creating the sun. From the remaining freely floating material, two microscopic particles came close enough to be attracted to each other by electrostatic forces. This was the moment of our planet's conception. The same process occurred throughout the forming solar system. Tiny particles of dust formed increasingly larger clumps. Eventually, the rocks grew large enough to be called planets, colliding with one another rather than breaking apart and reassembling in various combinations. But in each collision, there was a victor, and some of them became large enough to dominate the orbit they were moving along. All of this happened astonishingly quickly. It took only a few tens of thousands of years for tiny clusters of particles to grow into a planetary embryo with a diameter of 100 kilometers. In just 200 million years, or perhaps even faster, Earth essentially formed completely, although it was still in a molten state, subjected to continuous bombardment by floating debris. At this moment, about 4.4 billion years ago, an object the size of Mars collided with Earth, ejecting enough material to create the accompanying sphere of the Moon. It is believed that the ejected material coalesced into a loose mass within a few weeks, and a spherical rocky moon formed within a year, which has accompanied us ever since. Most of the lunar material comes from the outer layers of Earth, not from its core, which is why the Moon has so little iron, while we have plenty. Incidentally, this theory is often presented not as the newest, whereas in reality, it was first proposed by Reginald Aldworth Daly at Harvard in the 1940s. The only truly new aspect here is the attention people are now paying to it. When Earth was only about a third of its final size, it may have already begun to form an atmosphere, primarily composed of carbon dioxide, nitrogen, methane, and sulfur. These are hardly the substances we associate with life, yet it was from this toxic brew that life emerged. Carbon dioxide has powerful greenhouse properties. This turned out to be very fortuitous because, at that distant time, the sun shone significantly weaker. Without the greenhouse effect, Earth could have remained perpetually frozen, and life might have had nothing to cling to. But somehow, life managed to emerge. For the next 500 million years, the young Earth remained unyielding, bombarded by comets, meteorites, and various other cosmic debris that brought water to fill the oceans and the components necessary for the successful emergence of life. The environment was exceptionally hostile, but life somehow evolved. A tiny clump of chemicals jolted and came to life. 4 billion years later, humans began to ask questions. How did all this happen? Was this world shrouded in deep darkness? Let there be light. And then came Newton. Alexander Pope's epitaph was intended for Sir Isaac Newton. If you had to choose the most unfortunate scientific expedition of all time, you would surely find nothing worse than the Peruvian expedition of the French Royal Academy of Sciences in 1735. It was a group of scientists and adventurers led by hydrographer Pierre Bouguer and military mathematician Charles-Marie de la Condamine, who set out to Peru to conduct triangulation. The expedition was headed by La Condamine, with the scientific portion managed by astronomer Viguier and Pierre Bouguer. However, Viguier soon separated from the main party due to disagreements over methodology and was later caught embezzling funds sent from France. He also refused to share the results of the triangulation with his colleagues. The method chosen by the expedition was a common technique based on a well-known geometric fact. If you know the length of one side of a triangle and the sizes of its two angles, you can compute all the other dimensions without getting up from your chair. Let's take as an example that we want to find out the distance to the moon. The first thing we need to do to apply the triangulation method is to establish the distance between us. Let's say you stay in Paris while I go to Moscow, and we both look at the moon at the same time. Now, if you mentally connect the lines of the three main objects in our problem, that is, you, me, and the moon, a triangle is formed. Measure the length of the baseline between you and me and the size of both angles. The rest is easy to calculate since the sum of the internal angles of a triangle always equals 180 degrees. Knowing the sum of the two angles, you can instantly calculate the third, and more precisely, knowing the shape of the triangle and the length of one of its sides will give you the lengths of the other two sides. Essentially, this is the method that the Greek astronomer Hipparchus of Nicaea used in 105 BC to determine the distance from Earth to the moon. On the surface of the Earth, the principles of triangulation and surveying remain the same. Only the triangles do not reach into space, but lie side by side on a map. To measure the degree of a meridian, surveyors build a kind of chain of triangles stretched across the landscape. At that time, people were finally gripped by a strong desire to understand the Earth, to determine its age, mass, where it hangs in cosmic space, and to learn how it came into being. The goal of the French group was to contribute to resolving the question of the planet's circumference by measuring the length of one related meridian, or 1/360th of the distance around the planet along a line about 320 kilometers long, passing from the locality of Yaruki near a point outside the city of Ukrainka. All of this is now located on the equator. Almost immediately, things went awry, sometimes in a glaring manner. In Quito, the newcomers somehow incited the locals' displeasure and were expelled from the city by an armed mob throwing stones. Shortly after, a conflict over a woman resulted in the death of the expedition's doctor. A botanist went mad, and others died from fever or fell to their deaths in the mountains. Technical assistant Jean Gabin, the nephew of one of the leaders, Louis Gaudin, ran off with a 13-year-old girl and could not be persuaded to stay. Smart move. At one point, the group had to suspend work for 8 months, while La Condamine traveled to Lima to settle matters necessary for permissions. And to top it all off, La Condamine and Bouguer stopped speaking to each other and refused to work together. Wherever this ever-dwindling expedition party appeared, officials met them with the deepest suspicion, firmly convinced that this group of French scientists had traveled halfway around the world to measure the Earth. This seemed utterly nonsensical. Even 2.5 centuries later, this doubt remains relevant. Why not conduct their measurements in France and spare themselves the troubles and inconveniences of an Andean adventure? Part of this lies in the fact that in the 18th century, scientists rarely looked at things simply if a ridiculous but tempting alternative was at hand. Partly, it was a real problem that first arose before the English astronomer and two of us, Galileo. Long before Bouguer and La Condamine contemplated going to South America, with far less justification, Galileo was an exceptional figure. Throughout his long and productive life, he was a naval captain, cartographer, professor of geometry at Oxford University, deputy controller of the Royal Mint, royal astronomer, and inventor of the deep-sea diving bell. Strictly speaking, Galileo did not invent, but significantly improved the diving bell, which had first been used a century and a half earlier. He wrote knowledgeably about magnetism, tides, and the movements of planets. He lovingly described the effects of opium, invented a weather map and a current table, proposed methods for determining the age of the Earth and its distance from the Sun, and even devised a practical way to keep fish fresh out of season. The only thing he did not accomplish was discovering the comet that bears his name. He merely established that the comet he observed in 1682 was the same one seen by others in 1531 and 1607. It became Halley's comet only after 1758, about 16 years after his death. Actuarial tables are used to calculate pension benefits and life insurance premiums. They take into account mortality statistics across different ages. In a broader sense, current calculations refer to any rate calculations in insurance based on statistical data. However, despite all these achievements, perhaps Galileo's greatest contribution to the treasury of human knowledge was his involvement in a small scientific trio with two other prominent figures of the time. Robert Hooke, who is now more often remembered for being the first to introduce the concept and description of the living cell, and the great, dignified Christopher Wren, who was primarily an astronomer, and only later an architect, although today he is often forgotten. In 1683, when Galileo, Hooke, and Wren dined together in London, the conversation turned to the movement of celestial bodies. It was known that planets tended to move in a particular shape, an oval, which is called ellipses, as physicist Richard Feynman would express it, along a very specific and precise curve, but no one knew the reasons for such movement. Wren generously offered 40 shillings, approximately equivalent to 2 weeks' wages, to whoever first found an explanation. Hooke, widely known for claiming ideas that were not always his own, stated that he had already solved this problem, but refused to share the solution on the interesting and witty grounds that he did not want to deprive others of the pleasure of finding the answer themselves. Instead, he temporarily withheld the solution so that others could better appreciate it. If he had any thoughts on the matter, he left no evidence. However, he became so eager to find the answer that the following year he traveled to Cambridge and mustered the courage to approach mathematics professor Isaac Newton in the hope that he could help him. Newton was undoubtedly a strange individual, an extraordinarily outstanding thinker, but also reclusive, joyless, maddeningly irritable, and legendary for his absent-mindedness. It was said that in the mornings, after swinging his legs over the bed, he could sit for hours contemplating his ideas. And capable of the most unexpected antics, he created his own laboratory, the first in Cambridge, but then engaged in quite strange experiments. For instance, once he inserted a awl, a long needle used for stitching leather, into his eye socket and twisted it between his eye and bone as close as possible to the eye's bottom, just to see what would happen. Somehow, nothing happened, at least nothing serious. Another time, he gazed at the sun for as long as he could bear, hoping to understand how it would affect his vision, and once again he avoided serious damage, although he had to spend several days in a darkened room until his eyes forgave him for his experiments. Yet, over all these oddities and quirks, the intellect of a genius reigned supreme. Even when acting within the ordinary realm, Newton often displayed strange characteristics. During his student years, frustrated and limited by the constraints of traditional mathematics, he devised an entirely new form of differential and integral calculus, but remained silent about it for a full 27 years. In a similar vein, he worked in the field of optics, altering our understanding of light and laying the foundations of spectroscopy as a science. Again, he sought to distinguish himself through the results of his work. Despite his many talents, true science constituted only part of his interests for 3 decades. At least half of his working hours were devoted to alchemy and unorthodox religious pursuits. These were not merely amateurish activities, but serious passions that completely captivated him. He was a secret adherent of a heresy known as Arianism, characterized by the denial of the Holy Trinity. Ironically, at Cambridge, Newton belonged to Trinity College. The essence of Arianism, which emerged in the early 4th century, is not entirely accurately stated. Arians claimed that Christ was created by God the Father, and was not equal to him, but only similar. Therefore, contrary to the prevailing dogma of the time, the persons and hypostases of the Holy Trinity are not equal. He spent countless hours studying the floor plan of King Solomon's temple in Jerusalem, simultaneously learning Hebrew to decipher the original texts, convinced that they contained a mathematical key to determining the date of the second coming of Christ and the end of the world. He approached alchemy with equal fervor. In 1936, economist John Maynard Keynes purchased Newton's papers and trunks at an auction, only to discover, to his astonishment, that the overwhelming majority pertained not to optics or planetary motion, but documented his determined searches for a way to turn ordinary base metals into precious ones. A chemical analysis of a strand of Newton's hair in 1970 revealed mercury, an element of interest to alchemists, hat makers, barometer manufacturers, and, perhaps, many others. The concentration of mercury in Newton's hair was 40 times greater than the natural level. Therefore, it is not too surprising that he often forgot to get out of bed in the mornings. What Halley hoped to learn from him during his unplanned visit in August of 1684 can only be guessed, but thanks to later recollections from Newton's trusted associate, Abraham de Moivre, we have a description of this meeting, one of the most significant in the history of science. In 1684, Dr. Galileo visited Cambridge, and after some conversation, asked Sir Isaac what he thought the curve formed by the planets would represent if one assumed that the force of attraction to the sun was inversely proportional to the square of their distance from it. This was a reference to the mathematical concept known as the law of inverse squares, which Galileo firmly believed was fundamental to the explanation, but he was not quite sure how to demonstrate it. Sir Isaac immediately replied that it would be an ellipse. The doctor was greatly pleased and asked in astonishment how he knew that. The justification, he replied, I calculated it. Dr. Galileo immediately requested to see these calculations. Sir Isaac searched through his papers, but could not find them. Remarkably, it was akin to claiming to have found a cure for cancer and then forgetting where he had put the formula. At Galileo's insistence, Newton agreed to redo the calculations and publish a paper. He fulfilled his promise and then did much more. Retreating for 2 years of intense contemplation, he finally produced his masterpiece, Mathematical Principles of Natural Philosophy, better known as the Principia. And this is exceedingly rare. Only a few times in the history of human thought has observation been so insightful and unexpected that it is difficult to determine which is more astonishing, the fact itself or the thought that grasped it. The appearance of the Principia was one such moment. Through it, Newton instantly became famous. Until the end of his days, he basked in honors, becoming, among other things, the first person in England to be knighted for scientific achievements. Even the great German mathematician Gottfried Wilhelm Leibniz, with whom Newton engaged in a long and fierce battle for priority in the creation of differential and integral calculus, believed that Newton's contribution to mathematics equaled all that had been accumulated. No mortal can stand closer to the gods than he, wrote Galileo, expressing sentiments that were repeatedly echoed in the minds of his contemporaries and many others. The consequences. Although the Principia was called one of the most inaccessible books ever written, Newton intentionally made it difficult so that mathematical highbrows, as he called them, could not prey upon it. It served as a guiding star for those who managed to understand it. The laws not only mathematically explained the orbits of celestial bodies, but also defined the attractive force primarily responsible for motion, gravity. Every movement in the universe suddenly made sense. At the core of the Principia are Newton's 3 laws of motion, which clearly state that a body accelerates in the direction it is pushed, that it will move uniformly and in a straight line until another force slows it down or deflects it, and that every action has an equal and opposite reaction. His law of universal gravitation establishes that every body in the universe attracts all others. It may seem that this is not the case. However, sitting where you are now, you are attracting everything around you. The walls, the ceiling, the lamp, your beloved cat, with your weak, indeed very weak, gravitational field. It was Newton who realized that the attraction between two bodies, to use Weidmann's words, is proportional to the mass of each and inversely proportional to the square of the distance between them. In other words, if you double the distance between two bodies, the attraction between them decreases by 4 times. This can be expressed in a formula that, of course, holds no practical significance for most of us, but we can at least appreciate its elegance and conciseness. A couple of simple multiplications, a straightforward division, and bingo! You know your gravitational state, wherever you may be. This was the first truly universal law of nature comprehended and formulated by the human mind. That is why Newton is held in such deep respect. The publication of the Principia was not without drama. To Galileo's horror, as the work neared completion, Newton thunderously engaged in a dispute over priority regarding the law of inverse squares, and he refused to release the key 3rd volume, without which the first 2 held little meaning. Only through desperate shuttle diplomacy and the generous efforts of Galileo was he eventually able to extract the final volume from the unpredictable professor. But Galileo's troubles did not end there. The Royal Society, the so-called leading British scientific organization that had promised to publish the work, now withdrew, citing financial difficulties. A year earlier, the Society had supported the publication of an expensive and disastrous book titled The History of Fish, and believed that mathematical principles would hardly be in demand. Galileo, whose funds were not particularly ample, paid for the publication of the book out of his own pocket, while Newton, true to form, contributed nothing. To top it all off, Galileo, who had just agreed to take the position of Secretary of the Society, was informed that the Society could no longer afford to pay him the promised salary of £50 a year. Instead, he was paid in copies of The History of Fish. Newton's laws explained such a multitude of phenomena: ocean tides, planetary motion, the trajectory of cannonballs before they fell to the ground, and why the transformation of our planet at speeds of hundreds of kilometers per hour does not throw us into outer space. It took some time to gradually comprehend their significance. How fast you are rotating depends on where you are. The speed of the Earth's rotation varies from more than 1,600 kilometers per hour at the equator to 0 at the poles. In London, this speed is 1,038 kilometers per hour. However, one discovery almost immediately sparked controversy. This was the hypothesis that the Earth is not quite spherical. According to Newton's theory, the centrifugal force of the Earth's rotation should cause a slight flattening at the poles and a bulge at the equator, making the planet slightly oblate. This meant that the length of a degree of meridian in Italy would not be the same as in Scotland, specifically that this length would decrease as one moved away from the poles. This idea was unlikely to please those scientists whose measurements of planetary sizes were based on the assumption that it was a perfect sphere. And this assumption had prevailed for a century. People attempted to determine the size of the Earth primarily through meticulous measurements. One of the earliest attempts of this kind was made by the English mathematician Richard Norwood. Young Norwood traveled to Bermuda with a diving bell designed by Galileo, intending to collect pearls from the sea. The project ended in failure because there were no pearls to be found. Moreover, Norwood's bell did not work. However, Norwood was not one to disregard the lessons learned from experience. In the early 17th century, Bermuda was notorious among captains for being difficult to locate. The ocean is vast, Bermuda is small, and navigational instruments were utterly inadequate for overcoming this disparity. There was even consensus regarding the length of a nautical mile. In the vastness of the ocean, even the slightest error in calculations was magnified, causing ships to often miss their targets the size of Bermuda by a considerable margin. But Norwood, whose first love was trigonometry, and thus the measurement of angles, sought to bring a degree of mathematical precision to the art of navigation, and set out to determine the length of a degree. Departing from the walls of London's Tower, Norwood tirelessly walked 333 kilometers north over 2 years, stretching a measuring chain countless times along the way, and meticulously making adjustments for the rises and falls of the road's curvature. The final step was to measure the height of the sun in York at the same time of day, and on the same day of the year when he made his first measurement in London. From this, he reasoned, one could determine the length of 1 degree of the Earth's meridian, and thus calculate the length of the entire circumference. This was an almost absurdly ambitious undertaking. An error of the slightest fraction of a degree would distort the result by many miles. However, it turned out, as Norwood proudly proclaimed, that he measured the degree with a pinch of accuracy. To be precise, approximately to within 500 meters. The final figure was 110.72 kilometers per degree of meridian. In 1637, Norwood's masterpiece in navigation, The Seaman's Practical Guide, was published, immediately becoming popular. It went through 17 editions and was sold even 25 years after the author's death. Norwood returned to Bermuda with his family, where he became a successful planter, dedicating his free hours to his first love, trigonometry. He lived there for 38 years, and it would be nice to report that his days were filled with happiness and prosperity. In reality, life did not unfold that way. On the way from England, his 2 young sons were placed in the same cabin as the Reverend Nathaniel White, and somehow they traumatized the young clergyman to such an extent that he spent the rest of his career practically tormenting the Norwoods with any petty annoyances he could muster. The Norwoods were also troubled by their 2 daughters and their unfortunate marriages. One of them, possibly at the instigation of that very clergyman, constantly sued the Norwoods over trivial matters, causing great irritation and forcing them to make endless trips over the mountains to defend themselves in court. Finally, in the 1650s, the witch trials reached Bermuda, and Norwood spent his last years in terrible anxiety that his work in trigonometry, with its mysterious symbols, would be deemed a connection to the devil, leading to a horrific execution. It is known very little about him. Perhaps he truly deserved all the misfortunes in his later years, but one can only assert with certainty that he experienced them. Meanwhile, interest in determining the Earth's circumference shifted to France. There, astronomer Jean Picard developed an astonishingly complex method of triangulation using quadrants, pendulum clocks, zenith sectors, and telescopes to observe the movement of Jupiter's moons. A zenith sector is a portable astronomical instrument for accurately measuring the position of celestial bodies near the zenith. In 1669, after 2 years of traveling across France and conducting triangulation surveys using his method, he announced the refined size of 1 degree of meridian, 10.46 kilometers. This became a source of great pride for the French, but the result was based on the assumption that the Earth was a perfect sphere, which Newton now asserted was not the case. The situation became even more complicated when, after Picard's death, Giovanni Jacques Cassini and his son repeated his experiments over a larger area and concluded that the Earth is thicker at the poles than at the equator. In other words, that Newton was wrong in the opposite direction. This circumstance prompted the Academy of Sciences to send Bouguer and Locard to South America for new measurements, choosing the Andes because measurements needed to be taken near the equator to determine whether there was indeed a difference in the curvature of the Earth's surface, and because they believed visibility would be better in the mountains. In reality, it turned out that the mountains in Peru were constantly shrouded in clouds, and the group had to wait for weeks for clear weather to conduct their work. To top it all off, they chose one of the most inaccessible areas on Earth. Peruvians refer to their landscape as my Occident, highly rugged, and it was undoubtedly so, as the French had to climb some of the most difficult mountains in the world, which even their mules could not conquer. But to reach them, they had to cross turbulent rivers, cut through jungles, traverse a high-altitude rocky desert stretching for miles, and almost all of this was uncharted and far from any supply sources. But Bouguer and Locard were not lacking in perseverance. They diligently pursued their task for 9.5 long, harsh, sun-scorched years. Shortly before completing the project, they learned that another French group conducting measurements in northern Scandinavia, also encountering serious obstacles from marshy quagmires to dangerous ice flows, had discovered that closer to the poles, the degree was indeed longer, just as Newton had predicted. The Earth turned out to be 43 kilometers thicker when measured at the equator than when measured from pole to pole. Thus, Bouguer and Locard spent nearly 10 years obtaining a result they were not particularly pleased with, only to find out that they were not even the first to arrive at it. With little interest, they completed their surveys, confirming the correctness of another French group's results, and then, still not speaking to each other, returned to the coast and departed home on different ships. Before heading home, the first among European scientists undertook the extremely dangerous journey down the Amazon River. In Newton's Principia, there was another hypothesis that the plumb line would slightly deviate towards a mountain due to the gravitational masses along with the Earth. This was more than a curious fact. If one could accurately measure the angle of deviation and determine the mass of the mountain, one could calculate the gravitational constant, that is, the fundamental quantity for the force of gravity denoted by the letter G in the Latin alphabet, and also determine the mass of the Earth. Bouguer and Locard attempted to do this on the Peruvian volcano Chimborazo, but failed due to technical difficulties and their own disputes. So the idea was left untouched for 30 years until it was revived in England by the royal astronomer. Maskelyne, in his popular book Come On, Sable, portrayed a clockmaker, John Harrison, as a fool and a scoundrel for not appreciating his talent. And perhaps that was the case, but we are grateful to him for other deeds not mentioned in her book, among which is the successful method of weighing the Earth. Maskelyne understood that the key to the solution was to find a mountain of sufficiently regular shape to estimate its mass. At his insistence, the Royal Society agreed to commission a trustworthy individual to travel around the British Isles to seek such a mountain. Maskelyne had just the right person in mind: astronomer and geodesist Charles Mason. Maskelyne and Mason had become friends 11 years prior, while observing a very important astronomical event: the transit of the planet Venus across the solar disk. Tireless Halley had suggested many years before that if measurements were taken during one of these transits from selected points on Earth, one could calculate the distance from the Earth to the Sun using triangulation rules, and thereby calibrate the distances to all other bodies in the solar system. Unfortunately, the transit of Venus across the solar disk occurs very irregularly. They occur in pairs with an 8-year interval, followed by a century or more without any, and during Galileo's lifetime, not a single one occurred. However, the idea lingered, and when in 1761, nearly 20 years after Galileo's death, the time for the next transit arrived, the scientific world was more prepared for it than for any previous astronomical event. Scientists from all over the planet were ready to embark on this endeavor: Siberia, South Africa, Indonesia, the forests of Wisconsin, and many other regions. France sent 32 observers, Britain 18, and there were observers from Sweden, Russia, Denmark, Germany, and other countries. This was the first joint international scientific enterprise in history, and almost everywhere it faced difficulties. Many observers were halted by wars, diseases, or shipwrecks, while others reached their destinations only to find that their equipment was either broken or damaged by tropical heat. And again, by a twist of fate, the French turned out to be the most unfortunate participants. Gene Sharp took months to reach Siberia by carriages, boats, and sleds, carefully cradling his fragile instruments against his chest with every jolt, only to discover, at the end of his journey, that the last crucial segment was blocked by rivers swollen from unusually heavy spring rains, which the locals blamed on the astronomer himself. As soon as they saw him aiming strange instruments at the sky, Sharp managed to escape, but he could not make any useful measurements. Even more unfortunate was Guillaume Le Gentil, whose misadventures are wonderfully described by Tim Tay and Service in the book Coming of Age in the Milky Way. For Le Gentil, he traveled from France for the event to observe the transit of Venus across the solar disk. But due to various delays, he was still at sea on the day of the transit. There was no place to set up reliable measurements due to the rolling waves. Undeterred by misfortunes, he proceeded to India and stayed there to wait for 2 transits. In 1769, with 8 years to spare, he constructed a first-class observation point, checked all his instruments multiple times, and kept them in perfect readiness. On the morning of June 4th, 1769, the day of the second transit, it was clear, but as soon as the phenomenon began, clouds rolled in over the sun and remained there for almost exactly as long as the transit lasted: 3 hours, 14 minutes, and 7 seconds. For the women, he packed his instruments and set out for the nearest port. But on the way, he contracted dysentery and was ill for almost a year. Even worse, weakened by illness, he boarded a ship that nearly perished in a tropical cyclone off the coast of Africa. When he finally returned home, 11.5 years after beginning his journey without any results, he found that during his absence, his relatives had declared him dead and joyfully divided up his possessions. Compared to this, the troubles faced by the 18 scattered English observers around the world were minor. Mason found himself paired with a young geodesist, Jeremy Dixon. They apparently worked well together, as they later collaborated for a long time successfully. They were assigned to go to Sumatra and observe the transit from there. However, just 2 days after their departure, their ship was attacked by a French frigate. While the scientists were inclined towards international cooperation, the states were not. Mrs. Dixon sent a message to the Royal Society about the extremely dangerous situation at sea and asked whether it was worth canceling the entire endeavor. In response, they promptly received a cold rebuke, reminding them that they had already been paid, that the country and the scientific community were counting on them, and that refusing to continue the expedition would irreparably damage their reputation. Swallowing this bitter pill, they continued their journey, but en route, they received word that Sumatra had fallen into French hands, and they had to observe the transit from halfway around the Cape of Good Hope. On the return journey, they stopped at the remote island of St. Helena in the Atlantic, where they met Maskelyne, but their observations were again thwarted by cloud cover. Mason and Maskelyne became fast friends and spent several pleasant weeks compiling tide tables. Soon, Maskelyne returned to England, where he became the royal astronomer, while Mason and Dixon, now clearly more seasoned, set off for 4 long and perilous years to conduct a topographical survey of 390 kilometers of wild American territory to resolve a border dispute between William Penn and Lord Baltimore over their colonies of Pennsylvania and Maryland. As a result, the famous Mason-Dixon line emerged, later acquiring significant meaning as the dividing line between slave and free states. Although laying the line was the primary task, they also conducted a number of astronomical observations, including one of the most accurate measurements of a meridian degree in that century. This achievement was met in England with far more enthusiasm than the resolution of the border dispute between the capricious aristocrats. Upon returning to Europe, Maskelyne and his colleagues in Germany and France were forced to acknowledge that the observation of the transit of Venus in 1761 had essentially failed. One of the difficulties, paradoxically, was that there were too many observations, the results of which, when compiled, often entered into irreconcilable contradictions. Successfully recording the transit of Venus across the solar disk fell to James Cook, a little-known captain from Yorkshire, who observed the transit in 1769. After basking in the sun on the peaks of Tahiti, he was to map Australia and claim it for the British crown. Upon his return, French astronomer Joseph Lavoisier had enough data to calculate the average distance from the Earth to the Sun, just over 150 million kilometers. The 2 subsequent transits in the 19th century allowed astronomers to arrive at the figure of 149,559,000 kilometers. We now know the exact distance, 149,559,786 kilometers. The Earth finally found its place in space. This is the value accepted by the International Astronomical Union as the astronomical unit, the distance from the Earth to the Sun. It is known with an accuracy of plus or minus 30 meters. Over the course of a year, the distance to the Sun varies by plus or minus 2% due to the Earth's orbit not being perfectly circular. As for Mason and Dixon, They returned to England as heroes of science, but, for unknown reasons, ceased their collaboration. Despite their active involvement in many important scientific events of the 18th century, very little is known about them personally. No portraits have survived, and there are few written references. As for Dixon, the National Biography Dictionary mysteriously states that he was born in a coal mine, leaving readers to speculate about the circumstances of such an unusual birth. It adds that he died in Durham in 1777. Aside from his name and mention of a long collaboration with Mason, nothing more is provided. With Mason, there is clarity, and it is slightly less known that in 1772, at Maskelyne's recommendation, he accepted the task of finding a suitable mountain for conducting experiments on gravitational deviation from weight, and ultimately reported that the required mountain was located in northern Scotland, above Loch Tay, and was called Schiehallion. However, nothing could persuade him to stay there for the summer to conduct measurements. He never returned to the dust of research. The next mention of him relates to 1786, when he mysteriously appeared with his wife and 8 children in Philadelphia, apparently on the brink of poverty. After completing the topographical surveys, he had not returned to America for 18 years, and he had no known reasons to appear there again, nor friends or patrons who would be glad to see him. A few weeks later, he passed away. Since Mason declined to survey the mountain, this task fell to Maskelyne. In the summer of 1774, Maskelyne settled in a tent in a mountain valley deep in Scotland for 4 months to oversee a team of geodesists who conducted hundreds of measurements at all accessible points. To determine the mass of the mountain based on this multitude of numbers, a great deal of calculation was required. Mathematician Charles Hutton was brought in for this work. The geodesists at their village received a terrible confusion of figures, each representing heights at various points of the mountain or its surroundings. But Hutton noticed that if one took a pencil and connected the numbers representing equal heights, everything became much clearer. One could immediately get an idea of the overall shape and steepness of the mountain. Thus, Hutton invented contour lines of different elevations. By extrapolating the measurements of Schiehallion, Hutton calculated the mass of the Earth, 5 billion trillion tons, and from this, the masses of all other significant bodies in the solar system, including the Sun itself, could be derived. So, thanks to this one experiment, we learned the masses of the Earth, the Sun, the Moon, and other planets and their satellites. And in addition, we obtained contour lines. Not bad for a summer's work. However, these results did not satisfy everyone. The drawback of Hutton's experiment was that it was impossible to obtain accurate figures without knowing the density of the mountain. For convenience, Hutton assumed it to be equal to the density of ordinary stone, which is approximately 2.5 times greater than the density of water. But this was no more than a scientific assumption. The most unusual figure, at first glance, who drew much attention to questions about the Earth's axis, was a country parson named John Mitchell, who lived in the remote Yorkshire village of Thornhill. Despite his isolated living conditions and relatively modest position, Mitchell was one of the outstanding thinkers of the 17th century and was highly respected as a scientist. Among many other scientific endeavors, he grasped the wave nature of earthquakes, conducted a series of original studies in magnetism and gravity, and, remarkably, anticipated the possibility of black holes 200 years before others, a step that even Newton could not take. When the German-born musician William Herschel decided that his true calling in life was astronomy, he sought guidance on telescopes from Mitchell, whose kind and helpful nature attracted many scientists to him. Science about planets will forever owe him a debt. In 1781, Herschel was the first in modern times to discover a planet. He wanted to name it Gaia in honor of the British monarch, but the proposal was rejected. Instead, it became Uranus. However, of all that Herschel left behind in terms of ingenuity and influence on the development of science, nothing could compare to the mechanism he designed and built to measure the mass of the Earth. Unfortunately, he died before he could carry out the experiments. The idea and necessary apparatus were passed on to the outstanding, yet astonishingly shy, London scientist named Henry Cavendish. Cavendish deserves a separate book in his own right. Born into a wealthy titled family, his grandfathers were dukes. One was the Duke of Shrewsbury, the other the Duke of Cambridge. He was the most gifted English scientist of his century, and at the same time, the strangest. He suffered from shyness. According to one of his few biographers, limited by illness, any human contact was a source of profound discomfort for him. Once, when he opened the door, he found one of his Austrian admirers, who had just arrived from Vienna, standing on his doorstep. The Austrian began to excitedly mumble about his admiration. For a while, Cavendish took all these compliments as blows from a stick, and then, unable to bear it any longer, he ran down the path and disappeared behind the gates, leaving one door wide open. Only after several hours were they able to persuade him to return. Even in his own home, he communicated with the housekeeper through correspondence, although sometimes he dared to appear in society. He particularly enjoyed attending scientific evenings that were held weekly at the home of the eminent naturalist Sir Joseph Banks. Other guests were always made to understand that they should not under any circumstances address Cavendish or even look in his direction. Those who wanted to know his opinion were advised to casually stroll nearby and speak as if to the void. If their remarks were scientifically noteworthy, they might hear an indistinct response, but more often than not, they were met with an irritated squeak. Cavendish was very tall, and looking back, one could indeed see the emptiness and the back of Cavendish fleeing to a quieter corner. His wealth and inclination towards reclusiveness allowed him to turn his home into a large laboratory, where he could roam freely through all corners of physical science, studying electricity, heat, gravity, in short, everything related to the structure of matter. The 17th century was a time when science-minded individuals showed a deep interest in the properties of fundamental physical entities, especially gases. Electricity was beginning to be examined for what could be done with it, often displaying more zeal than common sense. In America, Benjamin Franklin became famous for risking his life by flying kites in thunderstorms. In France, chemist Pilatre de Rosier tested the flammability of hydrogen by taking it into his mouth and blowing it into an open flame. In one stroke, he demonstrated that hydrogen is indeed highly flammable, and that eyebrows are not a necessary feature of the face. Cavendish, in turn, conducted experiments in which he subjected himself to electric discharges of varying strengths, carefully noting the increase in painful sensations while he could still hold a pen or remain conscious, but not beyond that. Throughout his long life, Cavendish made a number of outstanding discoveries. Among many other things, he was the first to isolate hydrogen and the first to combine hydrogen and oxygen to produce water. But almost everything he did was accompanied by oddities and constant dissatisfaction from his scientific colleagues. In his published works, he often referred to experimental results that he had not previously reported. His reticence not only reminded one of Newton, but also surpassed him in many ways. His experiments with electrical conductivity were a century ahead of their time, but unfortunately, they remained unknown until that century had passed. In fact, much of what Cavendish accomplished was only recognized by the end of the 19th century, when Cambridge physicist James Clerk Maxwell, the founder of modern magnetism theory, took on the task of preparing Cavendish's papers for printing. By that time, nearly all of his discoveries had already been attributed to other scientists. Among many other things that Cavendish never mentioned to anyone, he discovered or anticipated the law of conservation of energy, Ohm's law, Dalton's law of partial pressures, Richter's law of equivalence, Charles's law of ideal gases, and the principles of electrical conductivity. And that is just a part of all his discoveries. According to science historian Crowther, Cavendish even astonished the research of Kelvin and Darwin regarding the slowing effect of tidal friction on the Earth's rotation, published in 1915, the communication of Barrow on local atmospheric cooling, Pickering's work on freezing mixtures, and some of Russ's studies on heterogeneous equilibria. Finally, he obtained results that directly led to the discovery of a group of elements known as noble gases, some of which were so elusive that they could not be detected until 1962. However, we are particularly interested in Cavendish's last known experiment, when, in the late summer of 1797, at the age of 67, he noticed a box of apparatus left to him, apparently out of pure scientific respect, by John Mitchell. The appearance of Mitchell's device resembled a Nautilus muscle-building machine made in the 18th century. It included weights, counterweights, pendulums, handles, and twisting metal cables. The core of the device consisted of two 350-pound lead spheres placed next to two smaller spheres. The idea was to measure the gravitational deviations of the small spheres under the influence of the large ones, which would allow for the first time the measurement of the elusive gravitational constant, from which the weight, or more precisely, the mass of the Earth could be derived. For a physicist, mass and weight are two completely different things. Your mass remains the same no matter where you are, while weight varies depending on how far you are from the center of another massive object, like a planet. Go to the moon, and you will be much lighter there, but no less massive. On Earth, for practical reasons, mass and weight are often equated, so both terms can be considered synonyms, at least outside the classroom. Because gravity holds planets in orbit, and things we drop with a thud fall to the floor, we tend to think of it as a very powerful force. But in reality, it is not. It is powerful only in a collective sense, when one massive object, like the Sun, holds another massive object, like the Earth. At the elementary level, gravity is extremely weak. Every time you pick up a book from a table or lift a coin from the floor, you effortlessly overcome the gravitational pull of an entire planet. And so Cavendish attempted to measure the attraction between very light objects. The key to success was precision. The room where the apparatus was located could not be subjected to the slightest disturbance, so Cavendish set up in a neighboring room and observed through a special peephole using a telescope. The work was unimaginably exhausting. It took 17 precise interrelated measurements, the completion of which took nearly a whole year. When Cavendish finally finished his calculations, he announced that the Earth weighs just over 6 billion trillion metric tons, using the modern measurement system, where a metric ton is 1,000 kilograms, or 2,250 pounds. Today, scientists have instruments so precise that they can determine the weight of a single bacterium, and so sensitive that they can malfunction if someone yawns from 20 meters away. But they have only slightly refined the results obtained by Cavendish in 1797. According to the most accurate current estimates, the Earth weighs 5.9725 billion trillion tons. The difference compared to Cavendish's findings is only 0.5%. Interestingly, all these measurements merely confirmed the estimates made by Newton 110 years before Cavendish, without any experiments. By the end of the 18th century, scientists had a very accurate understanding of the shape and size of the Earth, as well as its distance from the Sun and the planets. Now, Cavendish, even without leaving his home, added the mass of the Earth to this knowledge. Therefore, one might expect that determining the age of the Earth seems relatively straightforward. After all, the necessary materials lie literally beneath our feet. But no, people will split the atom, invent television, nylon, and instant coffee before they determine the age of their own planet.